tides is fundamental to safe and efficient navigation in tidal waters because many harbours are tidal, which means that they cannot be entered at all states of the tide, and it's necessary to perform calculations before entering or leaving in order to avoid running aground. We all know that the surface of the sea continually rises and falls. This movement is the result of tidal forces attributable to the gravitational pull of the moon and the sun. The lowest point in the cycle is called low water, and the highest, high water. The interval between low water and high water varies, but is around 6 hours and 13 minutes, so there are 2 high tides and 2 low tides, on average every 24 hours 51 minutes, with the time of high water and low water getting progressively later each day. The heights of high water and low water also change. Take a look at this graph for Portsmouth for the period 0000 hours on the 14th of August to 2400 hours on Friday the 16th of August, courtesy of the UK Hydrographic Office Easy Tide website. See how the time of the early morning high water moves back each day. The difference between the height of high water and low water is called the range. The range between high water at 0448 and low water at 1000 on the 14th of August is 2.9 metres, whereas the range between high water and low water the following morning is 2.4 metres, and 2.2 metres the next day. The reason for this variability is the ever-changing position of the Moon relative to the Earth and the Earth to the Sun. The Moon orbits the Earth approximately once every 28 days, and the combined centre of gravity of the Earth and Moon orbits the Sun approximately once every 365 days. The orbits are elliptical and are not exactly in plane. The Earth also rocks back and forth on its axis. The whole system takes 18.6 years to complete its cycle, and this period is known as the tidal epoch. If we ignore the Sun for a moment, you can see that the gravitational attraction between the Moon and the Earth will result in the surface of the oceans rising towards the Moon. The surface of the oceans is also raised on the opposite sides of the Earth. The reason for this is less obvious. Imagine a line equidistant between the points on the Earth nearest and furthest from the Moon. As you travel from this line towards the Moon, the gravitational pull increases. As you travel from the line away from the Moon, the pull decreases. This results in the oceans rising simultaneously on both sides of the Earth. When viewed from the North Pole, the Earth rotates anticlockwise once every 24 hours. So, if the Moon were stationary, any given location on the Earth's surface would experience high water, low water, high water, low water once a day. However, the Moon is also moving, travelling 1/28th of its orbit of the Earth every day, and 1/28th of a day is 51 minutes, so on average the tides get 51 minutes later every day. As the Moon performs its 28-day orbit of the Earth, its position relative to the Sun changes. From a new moon on day 0, the Moon waxes towards its first quarter 7 days later. Then on to a full moon after 14 days, when it starts to wane towards its last quarter after 21 days. before returning to a new moon on the 29th day. In the northern hemisphere, the lit side of the moon, when viewed from the Earth, is the right-hand side when it's waxing, and the left-hand side when it's waning. When the Sun, the Earth, and the Moon are approximately in line, at the new and full moon, they exert their maximum combined gravitational pull on the oceans, whereas when they are perpendicular to each other, at the first and last quarter, they exert their minimum combined pull. The Moon contributes approximately 2/3, and the Sun 1/3. So, at approximately the times of the new moon and full moon, the surface of the oceans rises and falls the most. We call the associated tides spring tides. And at approximately the times of the first quarter and the last quarter, the surface of the oceans rises and falls the least. We call the associated tides neap tides. So every 28 days there are 2 sets of spring tides and 2 sets of neap tides, leading to greater tidal ranges at springs than at neaps. Tide tables in nautical almanacs show neap tide days with blue dates and spring tide days with red dates. You can see here that the range in the early morning of the 21st is 4.4 meters, whereas the range on the 28th is 8.2 meters. Notice the first quarter symbol on the 18th of July, and the full moon symbol on the 26th of July. You can see that in this case, which is pretty typical for areas around the British Isles, neap and spring tides occur a few days after their associated moon phase. All the foregoing would hold good if the world were a perfect sphere, entirely surrounded by water, in which case the 2 high waters each day would be 2 very long shallow waves travelling rapidly around the Earth's circumference. But of course, the Earth is not a perfect sphere, and the only place on the Earth's surface that the waves can travel around unimpeded by the continents are in the southern oceans, south of all the major capes, Cape Horn, the Cape of Good Hope, Cape Lewin, etc. So all other tidal waves are harmonics of these waves, modified, amplified, and reflected by land masses, and bent by the Coriolis effect. The net effect is a huge diversity of tidal patterns. There can be an incredible difference in the tidal range between 2 places very close together. Some places apparently experience only 1 high water per day. Others, notably the central south coast of England, experience double high waters. Others, double low waters. Spring and neap tides can occur 2 days after their associated moon phase. Tidal predictions are therefore based partly on physics and partly on very long-term records of tidal heights in key ports around the world. Extreme meteorological conditions can also cause tidal heights to vary substantially from predicted levels. Unusually high pressure pushes the surface of the sea down, and unusually low pressure sucks the surface of the sea up. For example, at 10:25 on the 6th of December 2009, the predicted height of tide at Cowes was 2.18 meters, yet the actual height was only 1.42 meters, 0.74 meters below the prediction. Which was because this unusually deep low-pressure system northwest of Ireland was sucking up the surface of the sea there, preventing the tide from rising in the English Channel. At any given location, once in every 18.6-year tidal epoch, and ignoring extreme meteorological conditions, the surface of the sea will drop to its lowest level. This level is called lowest astronomical tide, or LAT. On any given British chart, there is a level known as chart datum, CD, which is a plane averaging lowest astronomical tide across all points on the chart. The difference between chart datum and lowest astronomical tide is very small, and, to all intents and purposes, insignificant. Note that whilst on British Admiralty charts chart datum is approximately lowest astronomical tide, some foreign charts use a different level. Of course, at any time other than the extremely rare occurrence of lowest astronomical tide, the surface of the sea will be somewhere above chart datum. The distance between chart datum and the surface is called the height of tide, HOT. The rise and fall of a tide is not linear, but approximately sinusoidal. In other words, it starts slowly, gradually accelerates, then slows down before the high and low tide. Tidal curves come in all shapes and sizes. Most are roughly sinusoidal, but others will have lumps and bumps. The shape of the curve might differ between spring and neap tides, and some are even centered on low water. Notice too that high water, or in some cases low water, are not necessarily in the center of the curve. This is because sometimes the tide takes longer to rise to high water than it does to fall back to low water, or vice versa. Take a look at this large-scale chart. The black figures written all over it are charted depths. For example, 12 or 1.5 meters. These are depths below chart datum. Notice how 1.5 meters is written on the chart. Charted depths are below chart datum, and, ignoring extreme meteorological conditions, should be the least depth ever experienced at this point. Areas colored green on the chart are above the surface of the sea at chart datum. See the figure 4.3 written here. Notice that the 4 is underlined. This is a drying height, and is measured above chart datum. In other words, at lowest astronomical tide, and ignoring extreme meteorological conditions, this point will be 4.3 meters above the surface of the sea. So the actual depth at any charted depth is the charted depth plus the height of tide. In this instance, the charted depth is 1.5 meters, and the height of tide is 6.5 meters. So the actual depth is 8 meters. Whereas in this case, we have a drying height of 4.3 meters and a height of tide of 6.5 meters, giving an actual depth of 2.2 meters. The average height of high water on a spring tide is called mean high water springs, MHWS. On Admiralty charts, everything between chart datum and mean high water springs is colored green, and everything above mean high water springs is colored yellow. Charted heights, for example the height of lights, are measured above mean high water springs. The average height of low water on a spring tide is called mean low water springs, MLWS. The difference between mean high water springs and mean low water springs is called the mean spring range. There are also mean high water neaps, MHWN, and mean low water neaps, MLWN, the difference between the two being the mean neap range. Finally, there is highest astronomical tide, HAT, which is the highest the tide will ever go, other than in exceptional meteorological conditions. Clearance heights, for example under bridges or power cables, are measured above highest astronomical tide. Clearance heights used to be measured above mean high water springs, and you will still find some old charts and particularly books that assert this. However, if you assume that the clearance is above mean high water springs, then you will always be erring on the safe side. You can find the heights of mean high water springs, mean high water neaps, mean low water neaps, and mean low water springs for various ports on many charts. However, only the very latest show highest astronomical tide. There is a table on page 12 of your RYA Training Almanac which gives values for the various ports and harbours on RYA charts 3 and 4. However, don't expect to find a similar table in a real almanac. In the real world, but not in the RYA Training Almanac, highest astronomical tide is given at the bottom of each page of tide tables in a nautical almanac. Now attempt questions 1 to 4 from exercise 2A. Please note, this lesson continues after the exercise. When navigating over an area of shallow water, you need to ensure that you have sufficient height of tide. Navigating over an area of shallow water, you need to ensure that you have sufficient height of tide to allow for your draft, distance from your waterline to the bottom of your keel, a safety margin, sometimes called clearance, and the charted depth. If your draft were 1.6 meters and you wanted to leave a safety margin of 1 meter, then you would, rather obviously, require 2.6 meters actual depth of water. We know that actual depth is charted depth plus height of tide. So imagine in this case that charted depth were 1.5 meters, which means that the height of tide required equals 1.1 meters. So the height of tide required equals draft plus safety margin minus charted depth. In this case, 1.6 meters plus 1 meter minus 1.5 meters equals 1.1 meter. Now attempt this question. What is the minimum height of tide necessary for a vessel with a draft of 2 meters to navigate into Portsmouth via the inner swashway, which has a least charted depth of 0.3 meters, allowing 0.5 meter safety margin? .2 meters, calculated as follows. Draft 2 meters plus safety margin 0.5 meters minus charted depth 0.3 meters equals 2.2 meters. When navigating over a drying area, green on the chart, the height of tide required is draft plus safety margin plus the drying height. In this case, 1.6 meters plus 1 meter plus 1.2 meters equals 3.8 meters. Now, what is the minimum height of tide necessary for a vessel with a draft of 2.5 meters to navigate over the eastern end of Bramble Bank, which has a drying height of 1.2 meters, allowing 0.3 meters safety margin? The answer is 4 meters, calculated as draft 2.5 meters plus safety margin 0.3 meters plus drying height 1.2 meters equals 4 meters. Before anchoring on a falling tide, you need to calculate the minimum depth of water you must anchor in now, in order that you do not go aground at low water. If you calculate the height of tide now, let's say 4.5 meters, and subtract from this the height at low water, let's say 3 meters, you know how much the tide will fall between now and low water, 1.5 meters in this case. So minimum depth to anchor in now equals fall plus draft plus safety margin. If we imagine a fall of 1.5 meters, as per the last page, a draft of 1.6 meters, and a safety margin of 0.5 meters, then the minimum depth to anchor in now equals 1.5 meters plus 1.6 meters plus 0.5 meters equals 3.6 meters. Now one for you. What is the minimum depth of water we must anchor in if the height of tide now is 5 meters, is 2.7 meters as LW, if our draft is 1.5 meters, and we wish to allow a safety margin of 0.5 meters? Well, the fall will be 2.3 meters, calculated as the height of tide now, 5 meters, minus the height of tide at low water, which is 2.7 meters, giving 2.3 meters. So the minimum depth to anchor in now is the fall, 2.3 meters, plus our draft of 1.5 meters, plus the safety margin of 0.5 meters, equals 4.3 meters. A very similar calculation can be used when you pick up a mooring or come alongside a berth to check whether you will be aground at low water. Clearance at low water equals depth now minus fall minus draft. If we imagine a depth now of 3.6 meters, a fall of 1.5 meters, and a draft of 1.6 meters, then the clearance at low water will be 3.6 meters minus 1.5 meters minus 1.6 meters equals 0.5 meters. Obviously, you will want it to be greater than 0. Will we ground at low water if our draft is 2.5 meters and we stay on a mooring where the depth now is 5.8 meters, the height of tide is 6 meters, and at low water it's 2.4 meters? The fall is 6 minus 2.4 meters equals 3.6 meters, and the clearance at low water will be 5.8 meters minus the fall, 3.6 meters, minus our draft of 2.5 meters equals minus 0.3 meters. So, yes, we will ground at low water. And of course, if you're anchoring in an area with a big tidal range, you're going to need to calculate the greatest depth of water that you'll experience during your time at anchor in order to lay out sufficient anchor cable. If you're using all chain, 4 times the maximum depth is generally accepted as the minimum. You can calculate the rise of tide by deducting the height of tide now from the height of tide at high water. Add the result to the depth now, and you have the maximum depth. Multiply this by 4, and you have the length of anchor cable to deploy. If we need to navigate under a bridge, or other overhead obstruction, such as power cables, we need to check that we have sufficient clearance. Clearance heights are measured above highest astronomical tide, or sometimes mean high water springs, which are, in turn, measured above chart datum. So, for example, if a bridge had a clearance height of 16 meters, and highest astronomical tide were 5 meters above chart datum, then the bridge would be 21 meters above chart datum. A vessel's air draft is the total distance between her waterline and the very top of her mast, including the VHF aerial. Cruising yachts typically have an air draft which is approximately 125% of their length overall, LOA. If it's going to be a close-run thing, check yours very carefully. Your clearance under a bridge is therefore calculated as clearance height plus highest astronomical tide minus height of tide minus air draft. So in this case, 16 meters plus 5 meters minus 2.5 meters minus 16.5 meters equals 2 meters. Another way of looking at this might be to ask, what is the maximum height of tide beyond which a vessel cannot navigate under a bridge, allowing a safety margin? Maximum height of tide equals clearance height plus highest astronomical tide, safety margin minus air draft. So in this case, 16 meters plus 5 meters minus 2 meters minus 16.5 meters equals 2.5 meters. If our air draft is 16 meters, what is the maximum height of tide beyond which we would be unable to navigate safely under a bridge clearance of 14 meters, where HAT is 4.5 meters and allowing a safety margin of 1.0 meter? The answer is 1.5 meters. You can download a copy of the tidal formulae from the Resources tab. Your depth sounder measures the depth of water below its transducer and can be calibrated to display the depth of water by adding an offset, or the depth under your keel by subtracting an offset. Make sure that you know if and how it's calibrated, and check it regularly with a lead line, which you should carry anyway as a backup. We'll be covering this in more detail in the lesson on electronic navigation. Determining an appropriate safety margin is one of many distinguishing attributes of an experienced seaman. There are many factors to consider. What you're really trying to establish is what the downside is if you do accidentally run aground. For example, running slowly aground on a soft, muddy bottom in calm conditions on a rising tide is only a minor inconvenience. Whereas running aground at speed on a rocky bottom, in rough water on a lee shore, or on a falling tide, could mean a serious threat to the lives of all on board, and total loss of the yacht. If you run aground on a falling tide, unless you get off very quickly, you're going to be there until the tide falls to low water and rises again above the height it was when you ran aground. If you ran aground just after high water, it might be nearly 12 hours. You really do not want to run aground at high water springs because it might be weeks before you can get off without suffering significant damage. This is called being neaped, and it has been known for vessels to be neaped for months if they ran aground at the top of an especially big spring tide. Those who are used to sailing in the muddy rivers and creeks of the Solent or East Coast need to recalibrate their thinking when sailing in rocky areas like the Channel Islands. Obviously, if the charted depth were 2 meters and the height of tide was predicted as another 2 meters, then, in calm conditions, give or take, you might expect a depth of 4 meters. However, even 1 meter waves will erode this by 50 centimeters, and, as every surfer knows, if the average wave height is 1 meter, every so often one of 3 meters will come along, and the last thing you need is to punch your keel up through the bottom of your boat as you fall off a wave. Remember, a lee shore is one you're being blown onto, and lee shores were greatly feared by sailors before auxiliary engines had some hope of clawing the vessel off. As you learned in the lesson about charts, some areas, close inshore, have not been surveyed for donkey's years, and it's very dangerous to assume that your GPS or chart plotter will keep you safe. Sandbars can move, and frequently do after storms. If the shallow channel you intend navigating is indistinct or poorly marked, you need a well-prepared pilotage plan which you can execute accurately. Allow an extra margin at night in poor visibility and strong winds. Extreme weather conditions, such as unusually low or high barometric pressure, or gale-force winds blowing continuously from one direction, can result in tides substantially above or below predicted levels. And what about type of keel? Thin-keeled yachts can sometimes be heeled over, using their sails or even crew weight in order to reduce their draft to help escape a grounding. But this will not work for bilge and wing-keeled yachts. On the flip side, bilge-keeled yachts can sometimes safely dry out on a firm, relatively level bottom to wait for the next tide. And skippers of yachts with lifting keels have a get-out-of-jail-free card. So, it's up to you. On a rising tide, in calm conditions and a soft muddy bottom, you can feel your way in or out of a creek at very low risk. However, sailing over rocks on a lee shore on a falling tide in big waves is an entirely different matter. We can find the time and height of high water and low water from tide tables. Almanacs only publish the times and heights as standard ports, which are major ports. Other harbours, estuaries and rivers are secondary ports, and if you need to establish times and heights at secondary ports, you need either a full set of Admiralty tide tables or a local set of tide tables, or to apply corrections to the times and heights for the associated standard port, or to use a computer. Admiralty tide tables detail the times and heights of high and low waters for over 230 standard and 6,000 secondary ports in the UK and Ireland, Europe, the Indian Ocean, South China Sea, and Pacific Ocean for each day of the year. The tables outline methods of prediction, the effect of meteorological conditions on tides, and provide additional information on exceptional tidal factors in each area. The tables are available from Admiralty distributors worldwide in 4 volumes and cost £30 per volume. Local tide tables are available from a number of sources, and if your home port is a secondary port, it's useful to obtain a set, perhaps from the local harbour master or chandlery. Alternatively, www.tidetimes.org.uk publishes tables for over 698 UK locations, and you can buy them individually online for just £1.49 each plus postage and packing. See the Resources tab. Many chart plotters and computer programs, including apps for mobile devices, can deliver not only heights for high and low water, but also the height of tide at any time between high and low water. UKHO offer Easy Tide, www.ukho.gov.uk, which delivers free predictions for up to 7 days ahead. See the Resources tab for a link. Of course, it's not a lot of use just knowing the height of tide at high and low water. We also need to be able to calculate it for any time in between, or to be able to establish what is the earliest or latest the height of tide will reach a given level. Imagine we need to establish the height of tide at Port Fraser at 0900 on Friday the 8th of March. If you go to page 48 in your RYA Almanac, you can see that there's a high water of 3.4 metres at 0654 and a low water of 1.2 metres at 1311. So we're on a falling tide, and at 0900 the height will be something less than 3.4 metres, but more than 1.2 metres. Now go to the associated tidal curve on page 51 and mark the time of high water into the box at the bottom in the centre of the curve. And then work forward to the time we're interested in, which is approximately 2 hours after high water. Now mark the height of high water on the scale at the top of the graph. And the height of low water on the scale at the bottom of the graph. Join the two with a straight line. The line is known as today's curve. Note that there are two curves, one in red for the pattern of the rising and falling tide on springs, another in blue for neaps. Sometimes the curves are coincident, at others they diverge. The best way to determine which curve to use is to calculate the range of this tide, which is the difference between the heights of high and low water. So, 3.4 minus 1.2 equals 2.2 meters. If we then look at the mean spring and neap ranges in the box in the top right-hand corner of the graph, we can see that a range of 2.2 meters is very close to the mean neap range. So we will use the blue neap curve. If the range of this tide comes out somewhere between mean spring and neaps, we can interpolate by eye between the two curves. However, we must never extrapolate outside the curves, meaning that if, for example, this were an exceptionally big spring tide with a range of, say, 4.5 meters, we would simply use the red spring curve. Now draw a line vertically up from the time we are interested in until it meets the neap curve. And from the point of intersection horizontally across until we meet the today's curve. And then up or down, doesn't matter which, to the scale on the top or bottom of the graph. And read off the predicted height of tide, which is 2.8 meters in this example. Now answer this question. You should get an answer of around 22:15 UT. Here's how we get there. If we examine a large-scale chart of the entrance to Port Fraser, or, better still, consult the pilotage notes in the almanac on page 46, we can see that the least depth in the inner sway is 0.7 meters. So, as you learned in the tidal theory lesson, the minimum height of tide necessary is your draft, in this case 2 meters, plus the safety margin, 0.5 meters, less the charted depth, 0.7 meters, equals 1.8 meters. From the tide tables for Port Fraser, you will discover that there is a low water at 19:38 and a high water at 01:58, early the following morning. And since the question asks, what is the earliest time on the evening of 2nd of January, you can infer that you are being asked to find the earliest time after 1938 you can enter. So, 01:58, or let's call it 0200, is entered into the graph as a time of high water. Height at 01:58 is 4 meters, and it's 0.8 meters at the preceding low water. We need 1.8, so we can drop a line down from there to today's curve, and then horizontally across to the tidal curve, which in this case is the same for springs and neaps, and then down to the time line, to find that the earliest we can safely enter is around 22:15. Note incidentally that each hour on the timeline is divided into 2 periods of 30 minutes and 6 periods of 10 minutes. All times of high and low water are given in the standard time for the time zone that the port is located in. Port Fraser is in the time zone UT, which stands for Universal Time, which, give or take a few microseconds and of political correctness, is what we used to call Greenwich Mean Time, or GMT, and is the standard time zone for the British Isles, along with such exotic places such as St. Helena, Ascension Island, and Tristan da Cunha. Then most countries employ daylight saving time, whereby they advance their clocks in the spring and retard their clocks in the autumn. In the United Kingdom, the clocks go forward 1 hour at 0100 on the last Sunday in March, and back 1 hour at 0200 on the last Sunday in October. The periods when the clocks are 1 hour ahead is called British Summer Time, BST. There's more daylight in the evenings and less in the mornings. The most important thing to remember is that for ports in the British Isles, the times given in the almanac are in UT. So if you're in BST and your watch, ship's clock, or these days mobile phone is to give the time in BST, then you need to add 1 hour to the times given in the almanac to make them correspond with the time on your watch, ship's clock, or mobile phone. The almanac tells you this in the top left-hand corner of the page. For example, when the tide tables give a high water time of 1342 on Sunday the 17th of March, your watch will show 1342. However, the afternoon high water on Tuesday the 2nd of April will occur at 1558 on your watch. If you examine the tables for Colville, starting on page 80, you will see that the time zone for Colville is given as -1 hour, and that if you needed to convert the times given to UT, you would need to subtract 1 hour from the given time. Colville is in the Southern Peninsula training world, and the Southern Peninsula mimics continental Europe, which is 1 hour ahead of UK time. In order to avoid confusion, you really need to adopt one of two strategies. Professional navigators reduce everything to UT, and ships will have 2 clocks on their bridge, one set to UT and the other to local time. Leisure navigators typically set their watch and ship's clock to local time, including daylight saving time if appropriate. In other words, your watch and clock read the same as the town hall clock in the port you're visiting. You still need to remember to add an hour to the times given in the almanac in the non-shaded areas, but at least you'll turn up at the restaurant on time, rather than arriving an hour late to discover a disgruntled restaurateur and your table long allocated to some last-minute chances. The circumstances where you're likely to make a mistake are when planning a passage across time zones. Imagine, for example, you are planning a passage from the Solent to St. Vast in Normandy. You would need to get your arrival time right, because St. Vast is tidal and can only be entered roughly 2 hours either side of local high water. If you get it wrong, there's nowhere else close by to take refuge, and you might have to hang around or anchor off for up to 8 hours, waiting for the lock to open. Which is not funny if you were intent on dining ashore on Saturday evening before returning to the Solent on Sunday morning. Well, they do say you learn through your mistakes. Well done. You've completed the lesson. Now go on to complete exercise 2A.